Hello, linear algebra. So I have to tell you, I'm so sad to not be there today. I realized when I came home that tomorrow or Tuesday, no, Wednesday, right now, when you're hearing this, was my day that I am at the hospital. I think you know that I am all getting a brand new titanium hip in March. And so today I'm at the hospital doing all my day full of pre-op testing, blood tests, x-rays, femur measuring, and then I apparently have to go to a joint class. So I am at school all day too, but it's just not the school I want to be in. So today you have Miss Sapleski. Everyone smile at her and say hello. But the lesson here is going to be from me by way of this screencast. The first thing we're going to do is remind ourselves that it's the day before Valentine's Day, which means we have romantic music as a backdrop. I love Valentine's Day, and I can't wait for Valentine's Day tomorrow when I have the day to hand out my individually chosen Valentines to each and every student. I hope you can hear this. This is romantic music as a backdrop for pre-Valentine's Day linear algebra. Okay, now let's go over homework first. Now, one of my sections, I know you ready. Oh, I should say this. Hold on before I go on. I left my stylus on my desk, and so what I had to do here was write it out on paper, took a picture, then I'm going to use my finger here to try and write. So we'll see how it goes, okay? We'll see. Oh, there we go. All right. Hi, Justin. You want to say hi?
Hello.
Okay.
Whoa.
I have to finish a class, okay? I'll be out in a minute to tuck you in.
Is it live streaming?
Yes. No, I'm recording. Okay. Hush, hush. Okay, stop pulling that like that. All right. I know that one class already talked about number 2, part B. Okay. Bye. Scram. Okay. So number 2 for my big section. I asked you about I sub n. So I sub n is a subset of W2 and V, but I sub n is not a subspace. And what I showed you here is that look at axiom 1. If you take I plus I, right, and both of these are in the subset I sub n, what you get here is a matrix that is not in I sub n. That's why I sub n is not a subspace. Okay, then we did number 3, okay. Number 3, oh dear, how do I move it up? Oh no. Hold on a minute. Okay, here we go. Number 3. Again, romantic music. Here's the question number 3. So V sub 3 was this set right there. And the conclusion for A is that V sub 3 is a subspace. Now you're going to look at my work here. Particularly, just look, axiom 1 right here, right? I chose U and V as just 2 polynomials. I showed that adding them does yield a polynomial, which is, of course, then in the set of polynomials. Here's axiom 6. Axiom 2 into 3 and 7 through 9, I would argue by observation, right? Pretty clear. Axiom 4, pretty simple, right? I mean, this is not a particularly difficult question, at least part A. Or difficult's the wrong word, but you know what I mean. So axiom 4 was met. Here's axiom 5, right? So part A, the set of polynomials, ax squared plus bx plus c is a vector space. Okay, now what about the subset W sub 4? So here we're talking about the case where polynomials where the coefficients plus the constant equals 4. Oh, we love Ed Sheeran.
And I can't sweep you off of your feet.
Okay, so now I said W sub 4 is not a subspace because, look over here, if you let these 2 items here, U and V, be 2 members of the subset, and then if you add the 2, you'll see that the coefficients here would equal 4 and not 2, right? Okay, Very good. Now for the new lesson. Let me pause this and upload my next sheet, okay? Okay, so here we go. The music was very distracting to me, so I've turned it off. So here's a question, and this is kind of what we're heading into next here. The kind of final finishing touch on this last new topic. So Adam Bazone asked once, like, what is this? How does this all tie into what we've been doing so far? Okay, well, here is part of the answer. So here's a question here. The question is, do these vectors right here span R space or R3, 3 space, okay? What does span mean? Span, when objects span a space, it's exactly what it sounds like. If you have a set of objects and they are said to span a space, what that means is through any number of combinations of those members of the set, the entire space can be represented, okay? And when we talk about combinations, we're specifically talking about linear combinations, okay? If a set of vectors, so our first example here has to do with vectors. If a set of vectors span a particular space, what that means is I can take a linear combination of any members, any 2 or 3 or 1, right? I can use these 3 members, and by combining them through 2 operations, addition and scalar multiplication, okay? That is the definition of a linear combination of objects. A linear combination of objects means a sum of scalar products, okay? If these 3 vectors span R3, that means I could add up multiples of 1, 2, or 3, all 3 of those vectors, and get any vector in R3. Okay, that's what I'm saying in this paragraph right here. Here is the mathematical translation of what I wrote in words, okay? And here's the new notation for you. So this right here, the span of these 3 objects. If the span of these 3 objects is the entire R3, all right, then it absolutely must be the case that there's a way that I could add up multiples of those 3 objects and yield any vector in R3. And I'm referring to any vector in R3 as this vector ABC. Okay, that's what it means for objects in a set to span all of a space. So I would say that, you know, if we kind of go back to kind of the Daffy example that we first did way back in the day of the set being the members in our classroom, all right? Do the members of our classroom, that set, do we span all of Shadyside Academy? Obviously not. There is no way that I could multiply you, right? Multiply a member and add it to a multiple of another member and get someone else. Already this analogy is falling apart. So for example, let's say I wanted to yield Mr. Logue, who is obviously not in our set. Is it possible to say add -3 Adam Bazones plus 2 Griffins? Will that give me Mr. Logue? No, it will not, okay? So the set, which is members in our classroom, do not span all of Shadyside Academy. And that was a terrible, terrible analogy. So here the question is, if this span of these 3 vectors is R3, then it must be the case that the sum of products or the sum of scalars of those objects would yield everybody in Shadyside, right? This here is kind of like the analogy of anybody in Shadyside right here, this one, right? Any vector in R3. Okay, let's see what that means. So what that means is we need to determine if there is a solution to this equation. And I don't know why this little thickie is here in the middle. That's awfully distracting. How do I get rid of that? I don't know. If I do this, no? Okay, so here it is. K1 times vector u plus K2 times vector w plus K3 times vector u. Do there exist, do there exist K1 and K2 and K3 such that I could add up these three, I can linearly combine these three and yield any vector in R3, 3 space. Okay, well, look what happens here. This just yields, oh my, a system of equations. Does that look familiar? Okay, does that look familiar? And look what we're doing now. Let's scroll down. Look at this matrix equation right here. This matrix equation, here's the coefficient matrix, matrix A. Here's K1, K2, K3, and here's ABC. Now, everyone, let me ask you this question. Is this system right here a homogeneous system? It could be, because ABC could be 0, 0, 0, because that absolutely is a vector in R3. But if we're looking at whether the linear combination, right, of these three vectors, u, v, and w, span all of R3, we cannot limit ourselves to A, B, and C being 0, 0, 0. We can't limit ourselves to a homogeneous system. So we have to remember here that this is not a homogeneous system. We want A, B, and C to be everything. Okay, what's the relationship here to determinants? Well, let's see. Let's take a look at the coefficient matrix. We know that for a non-homogeneous, quote-unquote, square system, right? Under what conditions will this system yield a unique solution? What's the answer, everyone? What's the answer? What's the answer? Here it is. If the determinant, right, if the determinant of the coefficient matrix does not equal 0, there will be a solution for any value A, B, and C. And what I did here is look at those little raw operations. I think triangulated matrix A. And once I triangulated matrix A, I took the product right here of the main diagonal, because that then gives you the determinant. So the determinant is -6, which is not equal to 0. So that means this system, regardless of what A, B, and C are, has a unique solution. What that means then is, I don't know why this is all fuzzy down here, but it means that U, V, and W, those three vectors, absolutely span R3. Okay, next example. Let's go down here. Just number 14 from your textbook. So here's the other thing. Just like objects in a set are not always vectors, the issue of spanning does not always refer to vectors. What's interesting is that your text just called vector f and vector g just cos squared x and sine squared x. I think they were maybe just using kind of the notation of vectors as we have, even in our axioms, right? And this question asks you to determine whether or not cos squared and sine squared, the span of cos squared and sine squared. Does the span of cos squared and sine squared, does it include, for example, cos 2x, 3 plus x squared, let's see, oh yeah, 1 and sine x, right? Okay, so let's take a look at some of these, and these are fairly straightforward. I mean, kind of all of linear algebra, at least your kind of exposure to it is pretty straightforward. It's not, the math per se isn't really that nitty gritty, okay? Well, let's see. Well, cosine double angle, cosine double angle back in the days of trig is just 1 cos squared x minus 1 sine squared x. So right away you see that cos 2x is in fact a linear combination of f and g. So cos 2x is an element of the span. Look at my notation here, okay? So cos 2x is included in the span of cos squared and sine squared. 3 plus x squared, it's interesting. When I was doing this piece of paper, writing it out, answering this question reminds me of, remember when you used to decompose rational expressions into partial fractions? So what we're doing is we're saying, is there a way for us to add up multiples of the members of the set, so A cos squared x plus B sine squared x? Is there an A and a B, right, that would yield 3 plus x squared? So what's interesting here is, as my little side note here is, remember, when you have an equation, if there exists an A and if there exists a B, right, those A and B have to exist for all values of x. So when you look at this equation here and you're asking yourself, is it possible for there to be an A? Is there possible for there to be a B? You're not solving for x, everyone. You're solving for A and B, right? So if you're solving for A and B, what that means is when you solve for A and B, those A and B values have to be valid for all values of x. So what that means is you choose your values of x savvily. This thing is going to drive me absolutely crazy, a little cross here. So here's my first choice. Let x equal 0, okay? If x equals 0, when you plug in x equals 0 here, you will see that a equals 3, right? And try another value of x. Like a savvy, again, choose savvily. I chose x equals pi. I first chose x equals pi over 2. You can see how I scratched that out, but you'll see why I changed in a moment. I chose x equals pi. If x equals pi, notice what happens is you're told here a equals 3 plus pi squared. Well, a can't be two different values. This is a contradiction. So we have just shown then that there is not an a and b value that will yield that will allow you to linearly combine the elements to get 3 plus x squared. And so 3 plus x squared is not included in the span of cos squared and sine squared. Okay, and then I just went through here and did the rest with parts C and D. And part C, our old friend, the Pythagorean identity. Look at that. That's a nice thing to remember, right? And then sine x is not in the span of f and g. And this is actually kind of fun to do because you know what I did here? I did this part right here and I was ready to kind of call it a day. But then I actually noticed something that because of just the use of the trig functions, my choice of x here, I kind of was playing to the fact that the signs will zero out. But then if I tried x equals pi over 2 and x equals 3 pi over 2, I did in fact get a contradiction right here. So sine x is not in the span of f and g. All right, okay, let me put your homework here. I'm going to tell you your homework, and I'm not going to write it because I can't write with my fingertip very well. So your homework here is going to be on span. It's going to be on span and determining spans, confirming or contradicting whether or not an element or an object is included in the span set. Page 201, what I would like you to do is numbers 8, let's see. Oh, 10's kind of fun. 8 and 10. And let's see. 8, 10, and 19. That's quite good. 19 is nice because 19 really throws you back to transformation matrices, okay? 8, 10, 19. Have a great rest of the day, and I will see you on Valentine's Day. Have a wonderful, wonderful morning. Goodbye. How do I turn it off? What happened? Oh no.